A nuclear reactor can run at temperatures hot enough to glow metal red, yet the entire system depends on one job that sounds almost simple: moving heat away fast enough to stay in control. The choice of coolant changes reactor pressure, fuel design, efficiency, safety features, and even whether the reactor can make more fuel than it uses. In this video we cover pressurized water coolant system, boiling water coolant system, heavy water coolant system, pressure tube coolant system, supercritical water coolant system, carbon dioxide gas coolant system, advanced gas coolant system, helium gas coolant system, high temperature gas coolant system, liquid sodium coolant system, sodium-potassium coolant system, lead-bismuth coolant system, molten salt coolant system, fluoride salt coolant system, chloride salt coolant system, organic liquid coolant system, liquid metal fast reactor coolant system, natural circulation coolant. If you want every major type broken down in one place, subscribe. We do this for everything. This is the world's most common reactor coolant system. In a pressurized water reactor, ordinary water flows through the reactor core and carries away heat, but it is kept under such high pressure that it does not boil even when it gets extremely hot. That hot water then passes through a steam generator, where it heats a separate loop of water that does turn into steam and spins the turbine. Keeping the radioactive reactor water separate from the turbine side is one reason this design became so popular for commercial power and naval propulsion. Most nuclear plants in the United States use this setup, and the same basic idea powers many submarines and aircraft carriers. It is a familiar starting point because it shows how a coolant can also act as a control-friendly heat transporter, leading naturally to a version that lets the water boil on purpose. A boiling water reactor also uses ordinary water, but here the design is simpler in one big way. The water is allowed to boil directly inside the reactor vessel. Steam forms right in the core, then goes straight to the turbine to make electricity before being condensed back into water and sent around again. That removes the need for a separate steam generator loop, which can cut down on equipment, but it also means the steam going to the turbine comes from the reactor side and must be handled accordingly. These reactors have been widely used in countries such as the United States and Japan. Inside the core, the amount of steam bubbles can actually affect the chain reaction, giving the reactor a built-in feedback effect as power changes. From there, it makes sense to look at a system that still uses water but swaps ordinary water for a heavier and much rarer version. A heavy water coolant system uses water made with deuterium, a heavier form of hydrogen, instead of the ordinary hydrogen found in normal water. As a coolant, heavy water carries heat through the core much like regular water does, but it also interacts with neutrons differently, which can let a reactor run on natural uranium without the fuel being enriched first. That feature has made heavy water reactors especially important in places where fuel flexibility mattered. In real use, the best-known examples are Canadian-designed systems, where heavy water often serves as both coolant and neutron moderator. Heavy water is expensive to produce, so plants work hard to recover and reuse it rather than lose even small amounts. The payoff is a reactor family with unusual fuel options and a distinctive engineering style, which leads directly to the pressure tube approach that often goes hand in hand with heavy water. Instead of putting the fuel and coolant inside one giant pressure vessel, a pressure tube reactor uses many individual tubes, each holding fuel and high-pressure coolant. The coolant, often heavy water but sometimes another fluid depending on the design, flows through these tubes, removes heat from the fuel, and sends that heat to steam generators or other power conversion equipment. This layout changes the whole reactor architecture. Because pressure is contained in many smaller tubes rather than one enormous vessel, the plant can be built, maintained, and even refueled in different ways. Some pressure tube reactors can be refueled while still operating, which is rare among power reactors and helps keep output steady. Canada's CANDU reactors are the classic real-world example. Once you see how much the coolant choice and plumbing shape the reactor itself, the next step is a water system pushed to even more extreme conditions: supercritical water. A supercritical water coolant system takes ordinary water beyond its critical point, where it is no longer clearly a liquid or a gas. In that state, the fluid can carry heat very efficiently without the distinct boiling process seen in other water-cooled reactors. The idea is to run the reactor at very high pressure and temperature, so the coolant leaves the core hot enough to drive turbines with better thermal efficiency, closer to some advanced fossil power plants. On paper, that means more electricity from the same amount of heat and a simpler steam cycle. In practice, the materials challenge is severe because the reactor environment is both hot and chemically demanding. Supercritical water reactors are still advanced concepts rather than common commercial machines. They show how far engineers have tried to stretch the familiar water route before moving to a very different family altogether. Gas coolants. In a carbon dioxide gas coolant system, the reactor core is cooled not by water, but by pressurized carbon dioxide gas circulating through fuel channels. The gas picks up heat from the fuel, then passes through heat exchangers or steam generators, where that heat is transferred to water to make steam for the turbine. Gas cooling avoids boiling inside the core and allows higher operating temperatures than many water systems, which can improve efficiency. Carbon dioxide was used in several early British reactor designs because it was available, workable at scale, and compatible with the graphite used inside those reactors. These plants helped establish commercial nuclear power in the United Kingdom. The equipment was large because gases are less dense than liquids and need more volume to move the same heat. That early carbon dioxide path evolved into a more advanced British version with hotter conditions and improved fuel, which is the next system. The Advanced Gas-Cooled Reactor, or AGR, is a specific development of gas cooling that uses carbon dioxide as the coolant, but pushes temperatures higher than earlier gas-cooled designs. Heat from the reactor core is carried by the gas to steam generators, where water is turned into steam to drive the turbine. The hotter gas means better efficiency, and the reactor uses graphite in the core along with fuel designed to handle the tougher conditions. AGRs became a major part of the United Kingdom's electricity system for decades, making them one of the most distinctive national reactor fleets ever built. Their concrete pressure vessels and unusual internal layout look very different from the steel vessels common in light water reactors. Even though this is a specialized branch of carbon dioxide cooling, it proved that gas systems could be practical at large scale. From here, the story shifts to another gas that is even more chemically calm: helium. A helium gas coolant system uses helium, an inert gas, to carry heat away from the reactor core. Helium does not burn, does not become corrosive easily, and stays chemically quiet even at very high temperatures, which makes it attractive for advanced reactor designs. The gas flows through the core, absorbs heat from the fuel, and then transfers that heat either to a steam cycle or directly to a gas turbine in some proposed systems. Because helium does not condense like steam, the machinery and pressure management are different from water-cooled plants. Real reactor projects in Germany, China, and elsewhere have explored or used helium in high-temperature designs. Helium's downside is that it is a small atom that can leak through tiny gaps, so keeping the system sealed matters a lot. Its clean chemical behavior opens the door to very hot reactors built not just for electricity, but also for industrial heat, which leads to the high-temperature gas approach. A high-temperature gas-cooled reactor is usually a helium-cooled design built to run much hotter than conventional reactors. The fuel is often packaged in tiny coated particles that can hold onto radioactive material even at very high temperatures, and those particles are embedded in fuel pebbles or blocks. Helium flows through the core, removes the heat, and sends it to a power system or industrial process. The big attraction is temperature. These reactors can potentially provide not just electricity, but also heat for making hydrogen, refining materials, or supporting heavy industry. China's HTRPM project is one of the most visible modern examples of this idea in real operation. The fuel itself is engineered almost like a miniature containment system around each grain. Once reactors move into these hotter regimes, engineers also start considering coolants that are not gases at all, but liquid metals with very different behavior. A liquid sodium coolant system uses molten sodium metal to carry heat from the reactor core. Sodium has an enormous advantage over water for certain reactor types. It can stay liquid at very high temperatures without needing extremely high pressure. That makes it especially useful in fast reactors, where engineers want a compact core and efficient heat removal without slowing neutrons much. The sodium flows through the core, absorbs heat, and then usually transfers that heat to a second sodium loop before making steam, keeping water away from the radioactive primary circuit. Real sodium-cooled reactors have operated in France, Russia, India, Japan, and the United States. The catch is that sodium reacts violently with water and can burn in air, so leak management becomes a central design issue. Even with that challenge, sodium remains one of the most studied advanced coolants, and it leads naturally to an even lower melting metal mixture, sodium-potassium. A sodium-potassium coolant system uses an alloy often called NaK, a liquid metal blend that stays liquid at lower temperatures than pure sodium. That makes startup easier in some designs because the coolant does not need as much preheating before it can circulate. Like sodium, NaK transfers heat very well and works without the extreme pressures required by water systems, which made it attractive for experimental reactors and compact systems. It has been used in some research reactors and in certain space reactor concepts where reliable liquid metal circulation in unusual conditions matters. The trade-off is familiar, but even more demanding. NaK is highly reactive with air and water, so containment must be excellent. Its unusual low melting point made it useful in niche applications rather than mainstream power plants. From there, the liquid metal story broadens from light reactive metals to much heavier ones, beginning with lead. Lead coolant system uses molten lead as the heat-carrying fluid. Lead is dense, conducts heat well enough for reactor service, and unlike sodium, it does not react violently with air or water, which removes one major hazard. It also has a very high boiling point, so the reactor can run at high temperature while staying near ordinary pressure. These features make lead attractive for advanced fast reactor designs intended for long fuel life and strong passive safety. The coolant flows through the core, takes away heat, and transfers it through heat exchangers to make power. The challenge is that molten lead is heavy and can be corrosive to structural materials if chemistry is not carefully controlled. Interest in lead-cooled reactors has grown in Europe, Russia, and elsewhere for future small and large reactors. One close relative of this idea has already seen real service in a very demanding setting, and that is lead-bismuth. A lead-bismuth coolant system uses a molten alloy of lead and bismuth instead of pure lead. The mixture melts at a lower temperature than lead alone, which can make operation and startup more manageable while keeping many of lead's advantages, including high boiling temperature and low chemical reactivity with air and water compared with sodium. The most famous real-world use was in Soviet Alpha-class submarines, where compact lead-bismuth reactors helped deliver very high speed. In a reactor, the alloy flows through the core, removes heat, and passes that heat to another system for power or propulsion. Engineers have to watch for corrosion and for the production of polonium-210, a radioactive byproduct that complicates maintenance. Even so, lead-bismuth remains a serious candidate for advanced fast reactors. After these heavy liquid metals, the next major family changes direction entirely and uses salts that are already molten. A molten salt coolant system uses a hot liquid salt instead of water, gas, or metal to move heat through the reactor. In some designs, the salt is only the coolant and the fuel stays solid, while in others the fuel is dissolved directly into the salt, combining fuel and coolant in one fluid. Molten salts can operate at high temperatures with low pressure, which is attractive because low pressure reduces the stored mechanical energy in the system. The salt flows through the core or fuel channels, absorbs heat, and then transfers that heat to a power cycle or industrial process. The famous molten salt reactor experiment at Oak Ridge National Laboratory in the 1960s showed that the concept could work in practice. Salt chemistry and corrosion control are major engineering issues, but the design space is broad and active today. That broad family includes several important subgroups, starting with fluoride salts. A fluoride salt coolant system uses molten salts based on fluorides, often mixtures containing lithium, beryllium, sodium, or zirconium fluorides depending on the design. These salts are popular in molten salt reactor research because they are relatively stable at high temperatures and can have favorable nuclear properties. As coolant, the salt circulates through the reactor, removes heat, and carries it to a heat exchanger. In fuel salt designs, uranium or thorium compounds can be dissolved directly into the fluoride mixture, turning the whole fluid into both fuel and coolant. Oak Ridge National Laboratory's molten salt work focused heavily on fluoride chemistry, and many modern startup designs still do. The challenge is not just heat transfer, but mastering long-term materials behavior in hot, chemically active salt. Fluoride systems are often the public face of molten salt reactors today, But another branch uses a different chemistry aimed especially at fast reactors: chloride salts. A chloride salt coolant system uses molten salts based on chlorides rather than fluorides. These salts are drawing attention for fast-spectrum reactor concepts because they can support reactor physics that differ from many fluoride-based designs. The basic job is the same. The liquid salt flows through the reactor, picks up heat, and transfers it to another loop or power system. In some concepts, fuel is dissolved in the chloride salt itself. Chloride salts can offer high-temperature, low-pressure operation, but they also bring difficult corrosion and materials problems, and some isotopes in the salt can complicate handling. Most chloride salt reactors are still in the research and development stage rather than commercial use. They represent one of the more ambitious directions in advanced nuclear engineering, showing how even within molten salts the chemistry matters enormously. Before returning to broad system concepts, there is one older path that tried replacing water with an oil-like liquid: organic coolants. An organic liquid coolant system uses carbon-based liquids, often hydrocarbon-type fluids, to carry heat away from the reactor core. The original appeal was easy-to-handle liquid cooling at relatively low pressure, with less corrosion than some water systems, and without the reactivity of alkali metals. The coolant flows through the core, absorbs heat, and then transfers that heat to make steam or drive another power process. Several experimental and demonstration reactors explored this idea in the mid-20th century, especially in the United States. In practice, the main problem was that intense radiation and high temperatures could break down the organic fluid over time, creating unwanted chemical products and making the system harder to manage. So while organic coolants were real and seriously tested, they never became mainstream. They remain a fascinating branch in reactor history, and they set up a broader category that groups several high-speed neutron designs under one cooling idea: liquid metal fast reactors. A liquid metal fast reactor coolant system is less a single fluid and more a reactor category defined by using a liquid metal coolant in a fast neutron core. In these reactors, the coolant is usually sodium, but lead or lead-bismuth can also fit the broader idea depending on the design. The liquid metal removes heat efficiently while avoiding the neutron slowing effect of ordinary water, which helps maintain the fast spectrum needed for breeding fuel or burning long-lived actinides more effectively. Heat is carried from the core to heat exchangers and then on to steam or other power cycles. Famous examples include the EBR-2 in the United States and BN series reactors in Russia. Some of these systems were designed to make more usable fuel than they consumed. This category shows that coolant choice is tied not just to temperature and pressure, but to the reactor's deeper fuel strategy. Next come two cross-cutting circulation methods that can apply to many coolant types. A natural circulation coolant system moves the coolant without relying entirely on pumps during normal operation, or at least during important safety conditions. Instead, the fluid circulates because hot coolant becomes less dense and rises, while cooler, denser fluid sinks, creating a continuous loop driven by gravity and temperature difference. This can work with water and, in some designs, other fluids as well. The big advantage is simplicity. Fewer active components mean fewer things that must keep working during an emergency. Many modern reactors use natural circulation as a backup safety feature, and some small reactor designs use it as a primary operating mode. The concept sounds gentle, but it can remove large amounts of heat if the system is arranged correctly. That passive behavior has become one of the most valued features in advanced reactor design. The final system is the opposite approach, where pumps do the heavy lifting to move coolant exactly where engineers want it. A forced circulation coolant system uses pumps or blowers to drive coolant through the reactor core and the rest of the heat transfer loop. This is the standard approach in many commercial reactors because active pumping gives engineers tight control over flow rate, temperature rise, and power output. Whether the coolant is water, gas, liquid metal, or molten salt, forced circulation can move large amounts of heat quickly and predictably. In a pressurized water reactor, powerful pumps keep water moving through the core. In gas-cooled systems, blowers push the gas. In sodium or salt systems, specialized pumps handle hot liquid fluids. The trade-off is that the reactor depends more heavily on powered equipment, so backup systems and emergency cooling design become essential. Forced circulation is a reminder that reactor cooling is not only about what fluid you choose, but also how you move it. And that completes the full map of reactor coolant systems in use, in history, and in development.